Morning at TMLS so far. Welcome to this session titled Optimizing Personal User Experience, presented by Tina Shen and Charles Zhu. A little bit about them. Tina is a dedicated MLE at Loblaw Digital with over 2 years of experience in the e-commerce industry. At Loblaw Digital, Tina has been instrumental in designing and building diverse machine learning solutions that deliver personalized recommendations across several e-commerce platforms, such as but not limited to Joe Fresh and Real Canadian Superstore. Her work significantly enhances user experiences through personalized and real-time product recommendations across various verticals. Charles is also a machine learning engineer at Loblaw Digital. He primarily works in machine learning productionization and ML pipeline governance for the company's Helios recommendation engine. Prior to working at Loblaw, Charles worked with the City of Toronto in analyzing transportation safety data and in astrophysics as a software engineer. Please give both of them a warm welcome.
I guess.
Oh, okay.
I don't actually know.
Sure.
Okay, that's fine.
You can introduce me.
Good afternoon, everyone. My name is Good afternoon, everyone. My name is Charles, and this is Tina. We are engineers with the personalization machine learning team at Loblaw Digital. And today we'll be presenting our method for optimizing personalized and browsing session reactive recommendations for our e-commerce verticals. In this presentation, I'll first cover how recommendations are used at LD and some of the challenges that we encounter. Tina will then do a deep dive on Neural Pattern Associator, our novel personalized and session reactive recommender. I'll then cover how NPA is incorporated into the Helios recommendation engine, our modeling and model serving platform. And finally, we'll touch quite briefly actually, on ongoing work. So we begin with recommendations at Loblaw Digital. In case you're not familiar, Loblaw Digital, or LD for short, makes and runs the digital services that are integral to Loblaw businesses. The line of business, that's what we call verticals, that we've worked with so far, that's our specific team has worked with so far, include PC Express, the grocery delivery and in-store collection service for Loblaws, Superstores, Zehrs, and many other grocery banners. The Shoppers Drug Mart and Pharmaprix online store, as well as the online store for Joe Fresh, our clothing retailer. There's a number of other products, such as PC Financial, that fall under the domain of Loblaw Digital as well, but we haven't yet worked with them. We generate and store recommendations through the Helios Sorry about that. We generate and store recommendations through the Helios recommendation, or HRE, recommendation engine, or HRE for short, which is a part of Helios, LD's microservices-based ecosystem. HRE is a suite of modeling and model serving components and is designed to be as flexible and scalable enough to serve recommendations across all of the LD services. If we add up all of the digital products that HRE is integrated with, we get approximately 2 million visits per day, and that corresponds to roughly 8 million requests for recommendations that HRE has to serve. Okay, HRE has to serve. What are some of these recommendations like? Well, many of them are based on item-based solutions. So they're item-based recommendations. We want to serve items that are similar or in some way related to the item the user is currently looking at. And we have a number of unsupervised and self-supervised solutions for this. On the Joe Fresh side, we use a contrastive learning technique called SimClear in order to find visually similar items of clothing to the item that the user is currently looking at. And on the on the Shoppers Drug Mart and PC Express side, we use a combination of 2 VEC models and BERT type models. Both of these are embedding generation pipelines. The 2 VEC ones use purchase data, and the BERT type models use product descriptions. Once we have these item embeddings, we can then perform vector similarity to generate similar items for a given item. Notably, those solutions are not personalized, and personalization is something the vast majority of e-commerce shoppers expect in today's retail environment. This is where user-based solutions come in. We have 2 models available to us here. A linear model called NCEPL-REC, which is a one-class collaborative filtering model that also depopularizes the most popular global recommendations. and a two towers-based deep model called UERS, which can incorporate user and item side information and therefore address the cold start issue. Notably, both of these model types require user histories to operate. And there's a challenge with that, because for many of our verticals, the majority of users are anonymous, and we cannot easily discern their historical information. Even if we could, historical data may no longer represent a user's current shopping intentions. If you've only bought winter clothing at Joe Fresh, and then you logged into the website today, then our personalized recommendations for you may not reflect what you're currently looking for. Finally, these recommendations are usually batch calculated on a weekly basis, and so are static throughout the entire browsing session. The solution is to switch to in-session recommendations. These rely on data from the current browsing session and therefore can be dynamically updated as that session progresses. Historical information can still be used. We can load the user's previous browsing session, for example, but is no longer required. A typical example of an in-session recommendation problem is grocery basket completion. Given a set of products the user's already added to their cart, can we predict the most probable additional items that they will add to cart during their current shopping session? And we can also translate this to just browsing, which, spoilers, is what we're doing with Joe Fresh right now. Given a number of items that the user has already browsed during their current browsing session, can we predict the most probable items that they'll browse during the remainder of the session? There are challenges when using in-session data as well, though. For one, users often will have multiple shopping intentions throughout their single browsing session, and those intentions could be interleaved with one another. For example, a user could be looking for breakfast items, and then switch to looking for baby supplies, and then back to breakfast items. Another possibility is that their shopping intentions could actually be multi-granular, meaning that some intentions are subsets of others. For example, someone shopping for an upcoming beach vacation may look for men's beachwear, women's beachwear, and kids' beachwear, all of which fall under the broader umbrella of beachwear. So we need a model that can address these complications in the data, and that's where MPA comes in, as well as Tina.
Thank you, Charles. Okay, so after listing all these challenges we might face when providing in-session recommendations, we now introduce our in-house recommendation model, Neural Pattern Associator, in short, NPA. This is addressing the challenges in modeling complex user intentions in online sessions. So this is a collaborative work between Loblaw Digital and Dalhousie University. Huge shout outs to all the authors here, especially the first author, Kai, and then Lan Uga is Professor Uga from Dalhousie University, and all the Loblaw Digital co-workers here. So why this name? For Neural Pattern Associator, neural stands for neural attention. We are using the attention mechanism to identify the multiple shopping intentions during the online sessions. So pattern stands for combination pattern, item combination pattern. These are corresponding to the user's shopping intention. An item combination pattern could be baby supplies, could be healthy breakfast, etc. Also, this model is identifying item associations based on the historical in-session interactions. These will be in-session user interactions with the items. So to identify the multiple item combination patterns, we are using a network of vector quantized attention, in short VQA modules. This will help us to identify within a session when there are multiple items that the user interacted with, which are the important item combination patterns that we should pay attention to. Also, for capturing the multiple granularity levels of combination patterns, we are stacking multiple channels and multiple layers of these VQA modules. This is in a similar fashion of how transformers work. Also, for modeling the interleaving shopping behavior, we are training the model with an any order autoregressive training method, but this will not be our focus of today's presentation. So first one, to identify the multiple combination patterns of items or shopping intentions, we are using the vector quantized attention here. So for vector quantized attention, what is vector quantization. This is a process of grouping similar data points, for example, shopping intentions, into clusters. For here, this is item combination patterns. Each cluster is represented by a single vector, or we call it code book, inside our model. So visualization, what this will look like is that we have a code book of all these combination patterns. Each of these combination patterns, for example, healthy breakfast, will be represented by a quantized vector in the embedding space. Second one, attention. Attention allows the model, this is familiar term for now at this point. Attention allows the model to focus on specific parts of the input data such that we know which part of the input data is more important and we pay corresponding attention to it. Vector quantized attention combine these two concepts. Instead of attending to individual elements, the model is attending to the cluster of similar elements. For here, this is the codebook of the item combination patterns. What this will look like for a real example is that for grocery basket completion task for items within a basket, for example, the milk over here, the model will learn a attention score vector towards all the possible combination patterns. For this one, the healthy breakfast combination pattern will have a higher attention score. So next, just to briefly summarize what VQA module is doing over here. So first, this module will identify each input item's attention score towards each combination pattern. So this is what we have visualized in the last slide. For an item in the basket, it will generate and learn an attention score, pay attention to different combination patterns that it could identify. In cases when there are multiple items in the current session, for example, multiple items in the basket, the model then learns an aggregated attention score towards each of these combination patterns. So then we get an aggregated attention score for this basket or for the ongoing session. Then we'll extract the possible combination pattern embeddings based on this attention score. This is an extraction process. Then we get the attention highlighted products from basket. For here, we know that, okay, in cases when there are multiple items in the basket, based on the identified combination patterns, we know which items are more important to identify the combination patterns and therefore to make the sequential predictions after that. So then this model will estimate the context of the basket. This is the last step over here in the module, based on the current status of the basket to fulfill an identified combination pattern. Quick example, based on the milk in the basket, bread is needed for recommendation based on the identified healthy breakfast combination pattern. So for next challenge, to identify the multi-granular shopping intentions, we are stacking these multiple VQA modules. So what we are doing is that we have described what VQA modules does, what it looks like. We are stacking multiple and parallel VQA modules together. So this forms a multi-layer and multi-channel MPA model here, illustrated on this graph. Layers are in this vertical line, and then for different channels, these are in this axis. So this is in a similar fashion with the design of the transformer models, where it's stacking multiple attention blocks. So through this different layers and different channels of the VQA modules, this model is gradually capturing low and high level context information through successive filtering. So remember that one of the challenges is that for multi-granular level of the intentions, we're just successively performing successive filtering of these context information through these layers. One thing to note is that for MPA model, it does not assume strong positional dependency. However, our model has the capability to perform a position encoding, just like all the other transformer sequential models. So for training MPA with random data permutation, this will emulate the behavior of order agnostic models. This will address the challenge of users interleaving shopping intentions. So for the evaluation of this in-house model, so for today's presentation, there are two main tasks that we will describe. So the first one is grocery basket completion. The second task is in-session fashion recommendation. So there are four experiment focuses that we will cover today. First is the model performance, for sure. And for capturing the multiple shopping intentions, the interpretability of the predictions, as well as the interpretability of these identified combination patterns. So for grocery basket completion, there are two data sets that we use. One is the public Instacart data set available online, and then another is the industry data set used by Loblaw Digital internally. So for grocery basket completion, the model input, what it will take in, is randomly selected items from the test carts. So these are the partial cards that we get from the test sets. The ground truth labels are the remaining basket items. So this is exactly what the objective of grocery basket completion is about. So there are various benchmark models that we compare to, starting from the most simple popularity-based recommendations, also going to more like general recommender systems, for example, VAECF. This is variational autoencoder for collaborative filtering. Also for other transformer-based models, for example, BERT for rec. So for these two data sets that we used for different metrics, precisions, recall, etc., for all these metrics that we use, the two variations of the proposed models are having significant model performance over the benchmark models. Next one, for capturing the multiple shopping intentions. In order to visualize how the model is capturing these multiple shopping intentions, we are showing the visualization of the activated combination patterns, which are on the x-axis over here, by the different attention channels in the MPA framework. So these are the 3 sampled attention channels. These are 64 dimensions combination patterns. So we can see that as items within a basket. This is the first one, it's a banana. The last one is watermelon. So these different attention heads are capturing different attention scores, activating different combination patterns or shopping intentions within these different channels. For example, this one is only activating 5 or 6 of them, and then for this one, it is activating more combination patterns. And as we can see, for different combination patterns, it is relatively different. So for example, when items are gradually added to carts, this combination pattern's attention score is decreasing. This combination pattern's attention score is increasing. So this shows the interpretability of how the MPA model is capturing the multiple shopping intentions or item combination patterns. So the second one, we want to show how interpretable is the predictions of the MPA model. So for here, what we are visualizing is for each input basket items, so these are 8 basket items, all the items within the basket, we are showing the self-attention score using this confusion matrix over here. On the right-hand side is the corresponding prediction. If it's green, then it's correctly predicted. For here, we are showing how the recommendation results are interpretable by the MPA models. For example, the first basket, the model is giving more attention towards the first item, correspondingly making the right recommendations. So this shows that for later on qualitative analysis or for any further analysis, our model is interpretable. Last one for this use case is that we are showing how the model is capturing the combination patterns. For here, for different identified combination patterns by the model, we're showing a word clouds of the top words in the product names that activated each of these combination patterns, like mostly. For example, this combination pattern is mostly activated by words or items that are related to milk, tea, mix, more like drinks. This combination pattern is more related with white rice or fruit, etc. So this shows the interpretability of the model in terms of how, like, what types of combination patterns or shopping intentions that it can capture and identify. So for in-session fashion recommendations, this is the second use case we'll talk about. So this will be a quick case study where we're showing how the model is capturing multiple shopping intentions. This will be a qualitative result. So for example, in an ongoing session, this user just started this session and has browsed a girl's sandals. The corresponding recommendations will be related with this current item, showing baby girls products, for example, shoes over here, dresses over here. Once this user started to browse items that are related with women products, that's the second shopping intention over here, the recommendation starts to blend in women-related products. For example, these are dress over here and women t-shirts over here. As more items are being interacted within the ongoing session, for example, user starts to browse sneakers, women's sneakers, these item shopping intentions are captured and more related recommendations are being recommended. But note that how the model still remembers that, okay, you still have shopping intentions for girls' products. So yeah, that concludes my part of the talk for our in-house recommendation model of NPA. So let's welcome Charles.
Thank you, Tina. So now that we have NPA, now that we have NPA developed and evaluated offline, how do we bring it into production? This is the architecture for the Helios recommendation engine. It is a collaborative effort between our team and our friends at the platform team, who build tooling for ML engineers. In particular, the serving framework, that big green box up top, was designed and built by the platform team. Boxes indicate individual components, such as ETL pipelines or model training. Arrows indicate actions, usually what data is being read from or written to. The logo for the technology utilized for each component is shown on its left. The cloud provider of choice for LD is Google Cloud Platform, so all of these are GCP technologies. The colors represent the broad workflow that each component supports, with the legend on the lower left. GCP provides Vertex AI pipelines. GCP provides Vertex AI pipelines for serverless MLOps workflows, and we utilize it to facilitate all of our model training and other recommendation generation tasks. Vertex pipelines are directed acyclic graphs written in Python, and for the simplest of calculations, we can write Python codes directly into the pipeline definitions. But for something as sophisticated as training MPA, we Dockerize a training task, and then we load it within a pipeline in order to operate it. We can then retrain that pipeline on a regular basis by scheduling that model training job. Pipeline artifacts from model training are written to our model artifacts and embeddings database. This uses two technologies. For model weights, they typically are fairly large in size, and we want them to last a long time, and so we put them into Google Cloud Storage. But for anything such as, say, user embeddings that we want to serve in real time, we use the Bigtable NoSQL technology. Now, we blow up that big green bar into its constituent parts. This is a look at HRE model serving. We serve recommendations by creating an API endpoint for each recommender. The LD services that interface with those API endpoints are typically the backends of websites and applications. To deploy endpoints, the platform team has built a serving architecture using Selden Core, an MLOps framework designed to deploy ML models as REST or gRPC microservices. In this diagram, each of the smaller boxes is a Docker container, and the arrows represent the flow of informations between containers. And of course, the thing as a whole is a directed acyclic graph, which we call a profile. When it comes time to serve NPA online, we load the model architecture into an inferencer container, and then we load the weights from the model artifacts database. When an API request reaches the inferencer, it then reads from a separate database for the browsing session of that particular user, and that information is fed into the model, which then makes a prediction. Prior to and after model inference, we perform filtering on the range of products that can be served. These filters are currently programmatic rules, and they are meant to make sure that we can satisfy business and legal requirements, such as we might not be allowed to serve two brands beside each other. These filters take care of those issues. You may also have noticed that we actually have multiple parallel branches of models and filters, and this is because our router combiner framework can route a single API request to multiple branches. And this, in practice, is useful for handling fallback. If we have a model that, for any reason, an edge or a corner case, is unable to generate recommendations, we can fall back to a different, often simpler model in order to still serve something back to the user. This architecture can also be used to orchestrate A/B tests, because you can just set the different control and treatment branches to different branches of the DAG, and then split traffic using the router. That A/B testing, as well as a number of other operations, is handled by the profile manager, which orchestrates the deployments on HRE serving. That profile manager, most notably, is able to dynamically scale up and down jobs as needed in order to satisfy incoming traffic. We typically aim for about 10 requests per second, and that actually translates to different amounts of compute for different models. But we can also scale up to hundreds. And speaking of A/B testing, we'd like to briefly touch on ongoing work. We are actually in the process of finalizing an A/B test for NPA, and we'll be going into production within the next week or so, hopefully. So in about 2 weeks' time, if you go to the Joe Fresh website and look at an individual product page and look under the customers also liked carousel, you may or may not be seeing results from NPA. Once the work surrounding initial public launch goes down, we plan on exploring different methods of loading additional user and item content into the model. And this is partly to solve certain edge cases or cold start issues, as well as just to generally improve the predictive performance of the model. Finally, we plan on expanding that model to other lines of business, especially PC Express, which the model was originally built for. We want to conclude by acknowledging all the effort and mutual support from both our team and the platform team that works with us. The launch of NPA into production definitely could not have happened without them.
Yes, and if you're interested in our publicly available published paper, you can scan the QR code on the right-hand side. And then again, huge shout out to all the team members who made this talk possible. Yeah, thank you all. Thank you, Charles. We now take questions.
Anybody?
That's fine.
Any questions?
Pretty clear.
Clear presentation then.
Yeah, must have been really good then.
Oh, one question
Good.
there.
Okay.
Hi. First of all, great presentation. I was just wondering, did you guys encounter any interesting challenges when you guys were first developing this, like something that you didn't expect?
For the model?
Yes.
Okay, that's a great question. So the development started about a year ago. I think not that much problem that we encountered. Yeah, it was converging pretty like expected, having normal curve, nothing overshooting. And then, yeah, because it is very similar design with the transformer model, so it's just like, how to say it? It's just like similar design, but we're just switching the internal design of the model. Yeah. So yeah, I will tell you if I remember anything.
Okay, no worries.
Did you notice a increase in sales when you did deploy this model?
We are just about to launch this model into production. So the A/B test will definitely tell us whether or not we improve sales. And yeah, fingers crossed. So we'll see.
But the offline performance is really good.
The offline performance
Yes.
is really good.
Thanks for the presentation. My question is that the code book, is that like what you guys came up with, or does the business team have any inputs with that?
For codebook, like
Yeah.
this one?
The categories or something?
Oh yeah, I think this is like some concept, like this is a concept that's very similar with the existing vector quantization like papers. So they have something that's called, not code book, but it's a very similar term. And then we just call it a code book. Yeah, that's like, but this is, when they use this concept, it's for other like image generation, like other fields, but this is specifically for recommendation field. So we change the name a little bit, and then that stands for the combination patterns over here.
Sorry, I have an additional question. So what was the involvement from the product manager? Because I'm a product manager, so in the personalization space, like, how is the product manager involved? Like, what was the interaction like with you guys?
This is
Good question.
that's a really good question. I'm trying to summarize because our product manager has been really helpful throughout this entire development period. But a bit of a complication is that the model was originally designed by a separate team, and we also switched product managers during development. And so I think in the last stages, the big lift from the product manager was coordinating all the other teams required to get this into production. Yeah, 'cause-
Thanks.
yeah.
That's the last question.
A really small one here. How did you account for various segments of users or the frequency at which the users shop? Like the shopping basket size is something, but then the frequency at which they shop is also different sometimes, right? So does the model account for that, or do you have to like train slightly different models for each customer segment?
What happens when one user shows up all the time in data? Because some users will shop more often than others. So is there a bias there?
But okay, I'm not sure entirely, but for the user segmentation for this first version of the model, it is addressing the problem when users are anonymous as well for ongoing sessions. So for this first version, we are just having different like data processing. We look at the data to see for different data sets, what are the optimal number of in-session interactions are to train the model. So for later on, we'll add in this user segmentation thing into the model design. So then it is personalized on next level. Yeah. Thank you.
All right. Thank you, Tina. Thank you, Charles. Another round.